Good afternoon. Welcome back to ECE 320A. Office hours have been voted on and established, and I went ahead, actually I needed a runoff election, but I said, no, I'm not going to do that. That's too many elections or too much voting. The Tuesday and Wednesday, I believe, at 9 to 11 tied, but I thought maybe it would be better to have two unique days, Wednesday and Thursday, instead of having 2 days, Tuesday and Thursday, that are basically the same scheduling, if that makes any sense. If we need to meet sometime other than office hours, see me after class or talk to me via email. Send me an email request and we can try to set up a different time. Homework number 1 hopefully is now available. That's due in a week. And that's based on what we're talking now, which is chapter 10 material. And that's what you should be reading. You should be covering all of chapter 10 to be able to keep up with what we're doing in class and what you'll be using for homework number 1. Today what I want to cover is I'm going to go over that example that we've done a couple of different times. Last time I think I asked you to find the complex power of the source. I didn't say whether it was supplied or absorbed by the source, and that's what you need to determine or calculate or compute. We'll also look at the load and line power, and maybe somewhere in there we will have a quiz. Then we will, after doing this complex power example, we will look at many different ways of calculating or determining complex power from many different variables, or deriving or developing complex power formulas. Given time, we will get into an example with multiple loads in terms of complex power. Let's begin with the system you probably now have permanently memorized after looking at it so many times this semester so far. And typically, if I remember, I will make my S's as a script S so that you don't get that confused with a 5. We're going to be talking about Laplace transforms, and that's an S. I will probably be using S's as scripts and not as a non-cursive form, which my S's start to look like 5s, and I don't want you to go, is that 5S or is that 55? Hopefully it will be clear when we start getting into that. So I'm going to try to be consistent with my S's as being script S's, where I've now converted that source to its RMS value. We took the maximum value and divided by the square root of 2. I believe your quiz last time, so now memorize that particular diagram or configuration. The quiz last time, I believe, was, remind me, what was the quiz? Or find the complex power of the source. I didn't say absorbed or delivered, I don't believe. I just said find the complex power of the source. Now in that particular terminology, so here was your quiz. Before we, well, is this absorbed or delivered? I'm sorry, yes, absorbed or delivered power based on if everything was moving in the manner that is indicated here, the complex power formula would have a plus or a minus sign associated with it. 50-50 chance, apparently. I hear some pluses and minuses. In our passive sign convention, we assign a positive power to power being absorbed, right? That's what we give a positive sign to. And a positive sign on that power means that the current, as drawn or as sketched, is entering the positive terminal of that element. Yes? So in this case, well, people will argue, well, the positive sign is entering, the current is entering the positive sign, but it's entering the positive sign after it's gone through the element. Is that making sense? So when I say, is the current going into the positive terminal, as I've drawn it, would have to be reversed in order for it to go into the positive terminal of the source. Is that making sense? I would have to reverse the direction of that current, I sub s, and I've indicated that it's a phasor. In order for that to be a positive power, that current would have to be going from right to left in the diagram. It's actually, if you just follow it around, there's only a series circuit here. I sub s bar is actually coming into the negative terminal first before it goes into the source, and then it exits out the positive. It's going in the negative terminal, so the power absorbed would be a negative. So if you have a negative power absorbed, that means it's actually supplying power to the system, that particular element. Is that making sense? In this case, our complex power, let me say S sub S, so there my S isn't a 5, it's an S, but the subscript S is a script S. This is now a negative V sub S I sub s star, or conjugate. We need to have that conjugated, and that's now our complex power. That's one formula for complex power, and we've assigned the minus sign, and you should probably say then absorbed. Or you could then say that this is V sub s as I've sketched it, supplied or delivered. So it's supplied by the source, it's delivered to the system. Is that clear? That being said, we're given V sub s bar. All we need to do is calculate I sub s bar and conjugate it. That's what I was looking for in this particular quiz solution. If I'm looking for the complex power of the source, if I can find I sub s bar, then I'm basically done. I just conjugate that and multiply it by V, which I already have been given, and that gives me the complex power of the source. I started talking about P's and Q's, and so people were going, well, you got the P's, find the Q's, and add them together. That's correct also, but that's a less direct way of finding this particular answer in this case. How do I find I sub s bar? You can find the equivalent impedance, divide that into the voltage, and there's your current. The equivalent impedance is the sum of all of those. And I won't typically bar Z. It's going to be a complex number, but I probably won't bar it or put a bar over it. This was now the line impedance plus the load impedance, or I now have 80 plus J60 for the total impedance of that system. Once I have, so this was the line piece, and this was the load impedance. I've combined those. Those were just connected in series. I can combine those easily enough. And now to find the current, which is in series, it goes through all of those elements. The same current does. I sub s bar as a phasor will be v sub s over z sub t. Can we do an analog or something similar to v squared over r? And that's to get the power, and we'll get into that later. When we start talking about all these complex power formulas, we'll see how the v squared over r generalizes to complex power. Okay? So yes, we can, but it's not quite that expression. Okay? But it's the same idea. You can, I think the question was, we know power is voltage times current, and in complex power, it's voltage times current conjugated. Now that we have that, maybe we can rewrite current as V over R, which generalizes to V over Z. And then we have a V times a V star, which gives you the magnitude of V squared. So if we had a real impedance, if Z sub t was purely real, let's say it's just 80, then we conjugate that. We would conjugate it, and we would have 80 minus J0 if we started with 80 plus J0. Theoretically, we conjugate it, but the conjugate of a real number is the same real number. Yes? Yes, so if you keep track of everything, the question was if you're using matrices to compute this, you would just need to have all of your elements maintained as complex numbers, and doing a matrix inverse, it will take care of itself. First exam, we'll probably get into maybe 10 by 10 matrices that will invert that are complex. So just heads up. We probably won't quite get there for the exam, which is scheduled for February 9th. Yes? But you should be able to understand that technique. Where are we? We can now convert this to polar, and if you have a calculator that does this for you, you might want to learn how to quickly compute or go from rectangular to polar, polar to rectangular. This is now a 3, 4, 5 triangle, effectively. So we have a magnitude of 100, and the angle, which direction is our impedance? In terms of if I drew a triangle relative to this impedance and I was going from rectangular to polar, that's what I'm doing visually. I'm sketching this impedance 80 plus J60. I'm going over here 80, and I'm going up here 60. And now I'm looking for that angle, which in this case is the angle of the impedance, and this is the length or the magnitude of that impedance. This gives me a feel for what I should expect my calculator to be spitting out at me. And I know that 60 is less than 80, and I better not be above 45 degrees when I compute my angle. And I better be bigger than maybe 5 degrees. And this is one of those classic angles that you'll probably commit to memory, but that's 36.9 degrees. Or our current is now, and I can actually divide 220 by 100. That's not too hard of a computation. The magnitude of that current is 2.2, and what's the angle? It's a negative 36.9. Now I'm ready to compute the complex power, let's say, delivered by the source, and that's just V times I sub S bar. or I'm sorry, I sub s bar star, and my stars are getting more and more ugly, but you can make pretty stars. You took your entire no, I was going to say K through 6, you were learning how to make pretty stars. So just remember how to do that, right? Keeping everything in track, what do I now need for I sub s star? I need to change the sign of that angle. That's all I need to do. And now it's becoming a positive angle when I conjugate I sub s. Or I now have 2.2 times 220. And my angle what does that mean? Well, what are the units on this complex power? Volt amperes. And now do I have questions or answers? Question. Why did we change the sign of our current angle? Because of this beautiful star right here. That's the conjugate. So when we conjugate something, that's when we have to change. So if it was in rectangular form, you have real plus imaginary. When we conjugate it, it's real minus that imaginary. In a polar form, all that means is we change the sign of the angle when we conjugate something. Yes, so we're taking it from a 36.9, now we're going a minus 36.9 if that was our orientation. Is that okay? And we started at minus, didn't we, with the current. The current relative to the voltage angle, I'm sorry, you can't see this on the audio, but you can see it in the classroom. Our voltage angle was here, wasn't it? At 0 degrees, horizontal. Where was our current angle? Minus 36.9. Which was leading the other? Or what was the current doing relative to the voltage? It's lagging. It's behind. So we had a lagging current. What would you expect the complex power to be if you have a lagging current? Inductive or capacitive? An inductor gives you lagging. And how do we interpret this? This is 484. That's our apparent power. That's the product of the magnitude of the voltage and the current. That's our apparent power. We might want to see what's the real power and what's the reactive power. And we can do that by plugging this into our calculator and going from polar to rectangular. We take 484 times the cosine of 36.9. That's our real power. Or we simply convert this angle through Euler and say this is cosine 36.9 plus j sine 36.9. And then multiply that times this magnitude of 484. Then we have our power in the two pieces, our real piece and our reactive piece. If we do that, we end up with 384, or resketch your triangle. You now have 484 going up at 36.9. The projection to the real axis gives you your P. The projection to the vertical axis gives you your reactive power. And you can see the relative relationship. Would you expect your reactive power to be the same size as the real, smaller, or bigger? Smaller, right? And we have a plus sign because that angle is positive. The units here are still volt amperes. If I pulled this out, this is my real part. This is my reactive part. And if I said, okay, this voltage is supplying 384 watts of power. It's also supplying 291 VARs. I need to tell you the sign of that. And I can say it's magnetizing. It's supplying. It's not absorbing or delivering. Actually, this is delivering 291 magnetizing VARs. It's giving the system that because it's an all-inductive load, isn't it? It has to deliver those magnetizing VARs. Questions on that? Do we know the power factor of the load? What have we computed so far? We have just found the current and the supply and the voltage supply was given to us. We've now computed the current going through that series circuit. If I wanted to find the power factor, well, what do I want to do first? I have a quiz problem. Why don't you guys now take out a piece of paper? Here's your quiz. We found the complex power of the source. I want you to find the complex power of the load. And this is now the load. And this I will refer to as the line impedance. For your quiz, what I want you to do, based on what we've done so far, hopefully that will make it a little less lengthy to compute. Now your quiz is to find the complex power of the load. And I appreciate those of you that are ripping this out. You're tearing off your little, whatever those are called, your jagged edges. That helps keep it all together so a little bit neater. That helps me a lot. Let me give you a couple minutes to do that. Not tear the thing off the piece of the paper, but to find the answer. To find the complex power of the load. Yes, so you already use what we've already determined. You already have the current determined. You have the supply voltage. Now I want you to find the complex power of the load. And you should be able to use what we've talked about so far to find that. I don't know that I said. The question was, did I say supplied or delivered? I think I said find the complex power of the load. I was very generic, so you need to tell me, is it supplied or delivered? I'm assuming that was your end thought process. Do you want another minute or not? Yes? Now we're doing paper airplanes, and I might do that. I sent you back too far, huh? Didn't I? Let's go ahead and talk about this. You can put that paper to the side, and that way I can see how far you were able to get in the amount of time given, which I gave you more than 2 minutes if you were really keeping track. We started going in the complex direction. Our apparent time that I gave you was 7 minutes. Actually, that was the actual time that I gave you and not 2. But in this case, if you wanted to first answer the question, what sign do I want to put in front of, well, maybe, let me go back. How are you attacking this problem? I wanted the power, the complex power of the load. How did you approach the problem? Okay, you could first find this voltage, V sub L bar. And how do you do that? This is Ohm's law, right? If you can't get started, what have we learned? Well, just make it simpler and go, what would I do if that impedance wasn't there? I would just multiply 78 times the current. Now you have a complex impedance, 78 plus J59. That quantity gets multiplied by the phasor, this complex number, I sub S bar, to give me V sub L bar as a phasor. Now that we have V sub L bar, what do we do? Then we multiply by the conjugate of the current going through that load. And what is the current going through that load? IS. It's the same current. All of these are in series. So you didn't have to recompute any current. There was no current division going on here. In this picture, what sign would I associate with this particular power? It's positive V sub L bar, I sub S bar star absorbed. If it turns out that some of your numbers are negative, then you know that, well, that's actually a piece that's supplied. But in this case, we would anticipate that this would all be absorbed power. In this case, I would say that the power of the load, sorry, I wanted to find it all, didn't I? So S sub L is going to be plus V sub L bar, I sub S bar star, and this is absorbed, where the plus sign is because the current as I've sketched it is going into the positive terminal as I've drawn it. But I haven't yet computed V sub L bar. You told me that that's what you wanted to do, so if we do that, V sub L bar is now this 78 plus J59. That's the Z of the load times I sub S bar, and I don't need to conjugate that, do I? This is Ohm's law, so that's just ZI. where I bar was, what was I bar? 2.2 at an angle of minus 36.9 degrees. And if we're multiplying, we probably want to convert everything to polar form. Then we can just multiply the magnitudes and add the angles. So we put this 78 plus J59 into polar form, giving us 97.8 at an angle of 37.1 degrees. And please don't tell my elementary school teachers about my penmanship. You can make yours cleaner, okay? That's the product that we need to compute, and that, if we do our, hopefully my math was correct, a little bit more than 200, 215.2, and the difference between 37.1 and 36.9. I'm adding those angles, and one is a negative, giving me 0.2 degrees. That's the voltage of the load. Now if I want the complex power absorbed by the load, that's when I have to put on the pretty star to my current. I need VI star. This now becomes whatever I just computed. And this was 2.2, and what was the conjugate? Well, I was initially negative. I conjugated, it goes up. Is that okay? And this becomes then 473.4 at an angle of 37.1 degrees. What are the units on that? That's volt amperes. And I might want that to be written in rectangular form to identify the real power and the reactive power. I now project onto the horizontal axis for my real part, the vertical axis for the reactive power, and I end up with 377.6 plus J 285.6 volt amperes. If I pulled that out, I could say that I have 378 watts absorbed by the load, and I have 286 bars of magnetizing bars being absorbed. Is that something like what you obtained? What's the power factor of the load? How do you find that? There's all sorts of ways to find this, actually. You can look at the difference between the voltage angle and the current angle of the load element, which is two pieces. It's the R plus JX, which is really what's the angle of that impedance. That's the difference between the voltage and the current, is the angle of the impedance. So you could find the angle of that impedance and take the cosine, and that would give you the power factor of the load. What we had also talked about, I think, was we said, oh, it's really the P of the load over the apparent power of the load, which was V sub L I sub S. Is that hanging out anywhere? That's the 473.4. So now I have a 378 divided by 473, or I have the cosine of 37.1. Hopefully all of these numbers are the same. This would give me, do I have it? So this is also equal to the cosine of 37.1 degrees, or 0.798. And what else do I want to know about my power factor? Whether it's leading or lagging, because when I take the cosine of a positive or negative angle, I'm just going to get a positive number, and I need to give you a little bit more information. I need to say, is it inductive or capacitive? Here you better look at it, unless I'm giving you a negative inductance, that I've got an inductor there. You know that that should be producing a lagging power factor. So you can anticipate the result. You can see that from here. You can see it by the sine of the angle. If you said the cosine of plus 37.1, that argument may get blurred from the cosine operation, but you can go inside there and say, oh, that was a plus sign on that 37. That says I have a lagging power factor. Here you know you have 285 in the vertical positive direction. This is now, if I said, what's the power factor, giving me 0.798, that would only give you 1 point out of 10. You need that lagging to give you all 10 points. I grade weird, don't I? Give you 0 points and then I add 1. What's up with that? No, you would get a large fraction of the points if you told me it was 0.798, but you also need that lagging to give me all the information. Is that clear? And you could get this many different ways. You could have said, oh, well, that's the power factor of the load is supposed to be the cosine of theta sub v minus theta sub I. What's the cosine of the voltage phasor? That was the 0.2, wasn't it? And what's the current? If we go back and find it somewhere, there's my current. That current's the same through all of those elements. Its angle is minus 36.9. I subtract that down here, and I get back my cosine of 37.1 degrees. There's many, many different ways to do that. What about the line power? Same computation strategy as you did for the load, right? You could find the load, or I'm sorry, the line voltage. You could find the drop from left to right across that line, 2 plus J1. You could now find that line voltage. What I'm saying now is maybe we want to know what this voltage is. V sub lowercase l bar. Once we have that, we can multiply it. There's a lot of different ways we could find this, but if I just said this is the, oh, and what's the sign of this power? I'm not going to scroll back. I was getting dizzy. But you can remember that current was going through the positive, or going into the positive terminal as we labeled it. This should be a positive, whatever V times I star gives us, absorbed. And if it ends up that one of those was a negative, that one was a negative absorbed, that just means it was delivered or supplied. In this case, we have V sub L, I sub L bar star, but I sub L is the same current that we've had all along. That's the I sub S bar, and we need to conjugate it. And anticipating what we're going to do in a little bit, I could just rewrite that V sub L as 2 plus J1 times I sub S bar, that's V sub L, times I sub S bar star. I'm just saying this is my V sub L. I'm sort of burying that into a new expression. What happens when you take a complex number and multiply it by its conjugate? You get its absolute value squared. In this case, we would have 2 plus J1 times I sub S squared. Or we could have done this a different way. What do we know about the power in the system? So this would be one way to find S sub L bar, and that has units of V sub L. I'm sorry, volt amperes. What is the magnitude of the current? That was 2.2. You square that and now multiply it by 2 plus J1, and that's your complex power of the line. What's another way of thinking about the complex power of the line? We already have 2 of the pieces. There's really only 3 pieces here. We have the power supplied, and that's being absorbed by these 2 other pieces, the load piece and the line piece. So we should be able to simply subtract the source and the line, the source and the load to obtain the line. Another way to find then S sub L bar, lowercase l, is to take the supplied power and subtract the load power. What was the supplied? Was it 3? I have 387 plus J290 minus, I'm going to say 378 plus J286, and end up with 9.4. Well, I'm obviously keeping some units and not keeping others. Wow. Anyway, if you do the math right, which I'm not guaranteeing I've done here, this is now the complex power of the line. Another way of computing it. You know, you're supplying it, and the 2 loads, the line piece and the load piece, are taking away from that. Questions on that? Let's look at basically your first homework problem, I think, which deals with a generic element where you're given the voltage and the current in the time domain and ask, find the complex power for this element, where I'm going to give you the voltage as 100 cosine omega t plus 15 degrees volts, and the current is 4 times the sine of omega t minus 15 degrees amperes. Does everybody understand the problem? What do I need to do in order to start working this problem? You could find theta v and theta I. The first thing you probably want to do, though, is make these trigonometric arguments, or I'm sorry, the trigonometric formula the same. You want to be working with all cosines or all sines. We'll probably deal with cosines in this class, because now we're basically comparing apples and oranges. We want to always be working with the same entity, meaning we need to convert this current so that this is now a cosine, so that now it makes sense to multiply these together and keep track of the angles. Otherwise, we're 90 degrees off in some way when we start looking at angles. First thing we'll do then is we'll convert to make them the same. Let's convert I of t. It's minus 15 minus 90, isn't it? So we have, what am I doing? I was trying to convert that. You guys need to wake me up. Well, there's a cosine. Minus 15 minus 90. This is now minus 105 degrees. If that's the case, what is the power P? The real power. Using our formulas that we had last time. We haven't really talked about those now, but this lecture, but what do you remember the power formula was if you're given a time domain current formula and a time domain voltage expression? We take the maximum magnitudes of the voltage and the current and scale them by 1/2, then take the cosine of something. What do we do? Cosine of theta sub v minus theta sub I. What I'm doing here is I'm taking 1/2 the magnitude of the voltage, that's the maximum value, times the maximum current value, times the cosine of theta sub v minus theta sub I. Or this is now 400 divided by 2 times the cosine of 15 plus 105, or 120 degrees. And that actually ends up being minus 1/2, so that I now have minus 100 watts. Minus 100 watts absorbed, right? By the convention, we had our current going into the plus terminal. So this is minus 100 watts absorbed, which really means this element is supplying 100 watts of real power. What's our Q? What was the reactive formula? Reactive power formula. It was exactly the same, except now you use the sine instead of the cosine. You now have 1/2 Vm Im sine, and it's going to be the same angle. It was theta sub v minus theta sub I, or we now have 200 sine of 120 degrees. And that's vars. If we wanted to now write that in words, this particular element or this network is delivering 100 watts to the two terminals, and it's absorbing magnetizing VARs at its two terminals. Questions on that? Meaning that particular load, or element I should say, or network, was minus 100 plus J 173.2 volt amperes absorbed. Is that making sense? If we absorb a negative, we're really delivering or supplying. So you could say that network is delivering 100 watts of real power to those terminals, and it's actually absorbing 173 magnetizing VARs, the reactive piece. And you'll be asked to do that many different ways on your first homework problem with V's and I's, but it's the same process. Just keep track of your signs and the formulas. Question? So why is it absorbed? The question is, why is it absorbed? The way I've sketched it maybe is a little weird, but now think of this element. Here's my positive sign, and here's the negative sign. This current, as I've drawn it, is entering the positive before it goes through the element. Because of that, my expression for the complex power is absorbed, because I have the passive sign convention. Is that making sense? Is everybody clear on that? That's absorbed power, and whatever happens with the product of I and V, it'll take care of itself. And that's what happened here. It ended up being minus 100 watts absorbed. That just tells you really you're giving that back to those two terminals. Yes, so a negative absorbed is the same as a positive delivered. Is that okay? I'm not trying to confuse you. I just want you to be clear on that. Question? Well, not real. The question was, does that tell you anything about the direction of the current? That just means that you didn't call it right relative to maybe the real power, but now you would have the same issue with the reactive power here. So it's, how do you want to draw your current? You could redraw the current and say, oh, well, the way I had it, it was a minus S, and it ended up being a negative or positive or whatever you needed it to be. Okay, so, but here you have two pieces, and they may not both be in the same direction, meaning the two pieces being your real power and your reactive power. Other questions? Let's look at some complex power expressions. We've already hinted at we start with what we were given. Is that correct, that formula? I need to conjugate the I. So that's how we started, but as I suggested before, we could rewrite voltage in terms of the current and the impedance. So I could say that that was Z I bar RMS times I RMS bar star. And this tells me then that I have I RMS magnitude squared. So if you don't believe me, go home and look at A plus JB times A minus JB. Multiply those out in the rectangular manner, and you'll see that you end up with A squared plus B squared. The J terms will cancel each other out. So you end up with the magnitude squared times Z. But what's another way of writing the Z of a generic element is its real part and its reactive part. And X could be negative. I'm not saying that X is always positive. X will be positive if it's inductive in nature. It will be negative if it's capacitive in nature. If I do this now, if I formally perform this operation, I end up with I RMS squared R plus J and what can we say about that formula? This is still the complex power. That's just P plus JQ, isn't it? So now we've learned another way of finding P and Q if we're given the current magnitude and the real part or the reactive part of our element. We can then compute its real power and reactive power. So this only holds for RMS. If you had the magnitude, so that's why if you had the maximum magnitude, you'd want to divide by the square root of 2 if your waveforms are sinusoidal. If there's something else, then you need to find the RMS value of that something else current formally, and that's a homework problem. So you need to remember how to compute the RMS of a generic waveform. Root mean squared. You square your function, you find the mean of that function, and then you take the square root of that over one period, and that will give you your RMS value. This piece is the P piece, and that's the Q. And all of these, so that this says now that the average power is I RMS squared R, and that would be in watts. Q would be I RMS squared X in VARs. All of these above have actually been in terms of, most of those, up here were current formulas, all in terms of current. Somebody, I think, initially in the beginning of the lecture said, what about V squared over R? Right? We didn't see that yet here, did we? We have I squared R, that's the real power. We have I squared X, that's the reactive power. And X could be positive or negative. Let's look at the voltage formulas. And we won't look at those as fully as we just did the other, but this is now the complex power formula, VI star. But now we want to rewrite I star in terms of voltage and impedance. Now we have VRMS times VRMS bar over Z. But we have to star that, don't we? That expression needs to be conjugated. And now we can conjugate the numerator, conjugate the denominator independently and use that information. Meaning we now have VRMS times VRMS star all over Z star. And that's our complex power, which we know what VV star does. If you knew the voltage across a couple of terminals and you knew the impedance, now you can compute the complex power without explicitly finding the current through that element. You can just use the square of the voltage magnitude and divide it by, you need to make sure you take the conjugate of the impedance of that element. And that's your generalization of V squared over R for power. But this is complex power. It's V squared over Z star. Questions on that? Complex power formulas. Let's now look at the idea of having a lot of different interconnected elements. So now let's look at the total complex power in a network. What's interesting and nice about power is we don't really have to worry, when we're looking at the total complex power, we really don't need to worry about parallel series combinations. We just need to find the power, complex power of each of these little pieces and add them up basically vectorially, keeping track of the real pieces and the imaginary pieces, and add those up and we can get the total. We don't have to worry about how they're interconnected. That's what I'm trying to say here in braces. The interconnection structure be it series or parallel or some other combination, is unimportant. If that's the case, let's look at this in a very general sense. Let's say that we have many different networks, and we'll subscript those or label those as network sub I or network I. Maybe I have 5 little networks in my overall system. One I'm going to call network 1, the other one 2, 3, 4, and 5. Each of those will have complex power made up of the real piece and the reactive piece. Meaning I'm going to have 5 P's and 5 Q's in my earlier example. If I generalize that to capital N, N is in New Mexico, then if I want the total real power of that system, P sub T, all I have to do is add up all of those individual pieces. That's all I'm saying by that summation argument. I now just have P1 plus P2 plus ... up to P sub N, capital N, and that's in watts. Likewise, I can do the same with my Q's. I have Q1, Q2, Qn. Units of that are vars, and I might put a little s inside the bracket, vars. My total power, total complex power, is what? It's P sub t plus J Q sub t, which is just this sum maybe I should change my index so that you're not confused. Let's say that this is L, and that would have units of volt amperes. And what I want you to realize is that the magnitude of the total, so there's the apparent complex power total. That's not the same as if you looked at each of these individual powers and summed up their apparent power. We're doing this vectorially. We can't add up the individual apparent powers and end up with the total complex apparent power. That makes sense? Just draw some vectors with a P and a Q, another P and a Q, and see if you get the same answer if you simply started adding up their hypotenuses without doing it vectorially. Let's look at an example of how we might do that. Suppose I have load 1 with 0 VARs and 100 watts. Load 2, let's say, is 700 VARs, and I'm going to say that's inductive, and this is 200 watts. Do you see how I can just play with the description of these to throw you some curves? And let's say that this third load is 1500 VARs, capacitive, (300 watts). Whoops. And maybe this voltage is 100. So this is load 1, this is load 2, and this is load 3. And maybe somebody says, what is this current? Wow, don't have any R, L's, and C's anywhere. Well, they're buried. So now we have to work with what we're given. Maybe your question is, what is I sub RMS bar? How would you maybe approach that problem? Do you know this voltage on the right hand on these two parallel loads? Do you know the voltage drop across those? No. So based on what I have just given you in terms of, oh, if I have a complicated interconnection of loads, I can take the real parts and their reactive parts and add those up and end up with the total load. in terms of real and imaginary, or real and reactive. And basically then I would be consolidating those three pieces, which aren't all in series, they're not all in parallel, they're interconnected in a different way. But you could think of this as being the power company right here. Here's the transmission lines feeding this industrial plant, and this plant has a couple of big loads in it, one being inductive and one being capacitive, is one way of thinking of that. And now you want to know what's the current that is needed to supply that much power to that system. And once you know the current, you could then, if you're the power company, you could figure out the complex power, and you could say, oh, well, I'm delivering so many watts with a certain power factor. And maybe you'll get taxed at a higher rate if your power factor is 0.8 or less, or maybe 0.9, depends on the power company. Maybe if your power factor is 0.9, you have a tax of 4%, and if it's 0.8, or between 0.8 and 0.9, maybe it's 10%. It may not be a linear tax, because that's not necessarily a linear relationship, this power factor. Does everybody understand how you might approach this? You can actually just put this into a table to keep track of it. You could say, well, let me just put this all together. So here's the solution. We're all about keeping things clean. I could say, here's the load. Here's the real power. Here's the reactive power. And here's the complex power for the different loads. And then I could say, well, I could also have the totals. I'm going to write these down. Wasn't this 100 for the first, 200, and 300? That was pretty easy. So the total real power was 600 watts. For the reactive piece, the first one didn't have any. That was a pure resistive load. What was the next one? Inductive. What sign do we give Q if it's inductive? We're going up, aren't we? That's positive. That was 700. What about the third load? That was minus 1500. So our total here was minus 800 VARs. And our total here would be 600 minus J 800. And now we know what the total complex power is. We know our V. We can compute our I, because we know VI star is S. We'll pick up at that point on Tuesday.